Good evening, everyone, and welcome to this evening's webinar entitled Hybrid Electric Drive, the Impact on Military Capability and Operations, hosted by the Germany region area. Germany group. So William Sutton from the UK MOD's DSTL will discuss the progress in the UK on exploiting hybrid electric drive solutions for world military platforms and how it can be exploited to transform mobility and widen military capability for operations. On the right-hand side of your screen, there is an Ask a Question tab where you can type your questions, and there'll be time at the end of the session for William to address these. So please do submit your questions during the presentation, and there'll be time for Q&A after. So without further ado, William, I'll hand over to you for your presentation.
Thank you very much. And on cue, the telephone rings in the other end of my study. The joys of virtual presentations. But welcome to this presentation. Some of you will have noticed the DSDL logo on the front sheet of the presentation. So just in case people aren't familiar with DSDL, I thought it was worth explaining who DSDL are, because that's who I work for, and a lot of the work I'm going to talk about has been supported and driven by DSDL. So DSDL, Defence Science and Technology Laboratory, is part of the UK Ministry of Defence. So myself and my colleagues, we're civil servants, and we're basically the S&T side of the Ministry of Defence. As you can see, we're quite a large organisation, over 4,000. And our roles include providing advice to the services, in my case, primarily the Army. We provide technical support to our procurement organisation. And perhaps most interestingly for many of us, we carry out a lot of research and analysis. And you'll notice the figures below. Out of our turnover of over 700 million, a good getting on for half of that is spent with industry. So much of our research we do in collaboration with industry, and you'll see that later on in my presentation. In terms of capabilities, we cover all aspects of defence. So I sit in the land systems area, but we do the other domains. We do space and a lot of the more sort of technical areas, like AI and data science, sensing, specialist areas such as chemical defence and cyber. So that's who DSDL is, and who I work for, so in case you weren't aware. Anyway, what I'm going to do in the short presentation is I'm going to talk about the mobility requirements for military platforms. And as engineers, it won't surprise you to know that what you end up with is some design conflicts. And then I'm going to talk about how we're, particularly by trying to exploit the flexibilities of electric drive, trying to resolve some of those conflicts so that we end up in the future with more optimized platforms. But mobility is really what tanks are about. People ask me, what do I do? I say I do tanks. And if you go right back to the early tanks, particularly the very first tanks used on operations, the British heavy tanks, they were designed to cross difficult terrain. They were tracked so their ground pressure was reduced. They could cross soft soil. They were optimized to cross no man's land, and they were shaped. The sprockets at the front of the vehicle were high for climbing parapets. They were long, and some even had extensions so that they could cross wide trenches. So right from the start of tanks, mobility was absolutely key, and it's been a key driver for armoured vehicles ever since. I'm just going to talk about three aspects of mobility. We tend to sort of focus on the bottom, on the tactical mobility, because we like seeing pictures of tanks and armoured vehicles splashing through muddy puddles, but actually mobility can be broken into three areas. So there's strategic mobility. The British Army is an expeditionary army designed to be deployed anywhere in the world. And strategic mobility is all about how do you get the men and equipment to where they're needed. And then once they got there, there's operational mobility. So that's the ability to move rapidly from the point of entry, whether that's an airfield or a port, to where the tactical effects are required. And operational mobility also drives that ability to do rapid, long operational moves over long distances to outflank and outmaneuver the enemy. And any sort of historians of the World War II Western Desert will be familiar with that sort of concept. And then finally, tactical mobility. That's the ability to move anywhere on the battlefield, what we would term as freedom of movement, and being able to move freely depending on sort of natural barriers or man-made barriers. So if we start with strategic mobility, that's really all about weight and size of the platform. And if you're going a long way, the most efficient way of getting a large force to where you need it is by sea. You can use large ferries to take a lot of vehicles, a lot of support equipment with you. But it also includes landing craft for little war operations. And related to sort of transport by sea, actually, if you can design your vehicle small enough to go into ISO containers, that actually can make loading and unloading and protection during the voyage easier. So sea is a very important means of transport, particularly if you're going a long way and you need to take a large force with you. Air is probably the most critical one in terms of weight. Air includes the ability to transport equipment inside aircraft, or for smaller equipment, it's actually underslung from helicopters. As I say, weight is absolutely critical, not just what weight the aircraft can carry, but what can the loading ramps take. And often, although a vehicle might meet the weight class in aircraft, there are often very stringent loading limitations on the load bed of the aircraft. I think the other thing to bear in mind is often people will claim their platform is C-130 compliant, which means actually they can fit it in a Hercules that can actually take off. But if you look at the numbers, often the range is very, very short. So it's not just looking at what's the maximum weight an aircraft can carry, but looking at the range it can usefully fly with that weight in it. Size constraint, obviously the internal dimension of the aircraft are important. You've got to remember, normally if you're going into an aircraft, you're going up some sort of ramp, so overhangs when you're loading and unloading are important. But also you can't just fill the whole the load bay of the aircraft. There's got to be room for movement for safety reasons, and you need to be able to tie down the cargo. So weight and size important for air, but not quite as straightforward as it might seem. Rail, that's a very efficient way of moving a lot of vehicles across land, defined by the rail gauge. And actually, in terms of a lot of armoured vehicles, so things like the Challenger tank, the Warrior, infantry fighting vehicle, it's actually the rail gauge which has been the main driver for the sort of silhouette of the platform. And of course, in the UK, we have a problem that our rail gauge is much more demanding than the European rail gauge. And then finally, you can move platforms by road, and those who live in the south of England could well be familiar with stuck behind a convoy of tank transporters on the A303. But what you have to remember is once you put a 70-ton tank on a tank transporter, you've probably got a vehicle that weighs over 100 tons. So you've got to consider carefully the local infrastructure and be cognizant of any height restrictions. So that's strategic mobility. Operational mobility, as I say, it's that ability to move quickly both to the operational area and around the operational area. You can use transporters to do that. That's particularly beneficial for tracked vehicles. But the ability to self-deploy is very valuable. Yeah, if for every tank you take, you have to take a tank transporter, that means you're taking twice the number of vehicles plus additional crew. So self-deployment is a good thing. Operational mobility is obviously impacted by how quickly you can go. And that's not just top speed, but the sustainable speed, endurance, the range of the platform, but also crew conditions. Notwithstanding the benefits of band track, I wouldn't recommend going too far in a tracked vehicle and being expected to be in pristine condition when you get there. And obviously, if you're moving around in other nations, you would want to use their existing infrastructure without damaging it. I think tactical mobility, that's the one perhaps we all tend to focus on. As I suggested earlier, as illustrated in the picture, we like seeing tanks splashing through muddy puddles and showing how they can go cross country. Tactical mobility is really important for the close combat battle. That ability to attack from unexpected directions, that ability to take direct routes rather than having to take long detours to avoid given areas of ground. In armoured vehicles, you want to take up good fire positions, good observation positions where you can see a long way, where you can remain concealed so that only your sights or your weapon are visible above the brow of a hill. Good tactical mobility will enable you to get to the best position for what you need to do, and you're able to get to high ground and dominate the high ground. The other really important thing about tactical mobility is it gives you that freedom of movement. If you're in vehicles which can only go in limited places, it's very easy for the threats to identify where you can go, and along those routes of advance, that's where they put set up the ambushes. That's where they put the mines. So that freedom of movement really is important from a survivability point of view. So we drill down a bit more into performance requirements. Maximum speed, both on road and cross country, and just to sort of blow the trumpet for British equipment, the picture on the top, it is a Challenger 2, which I would argue has probably the best tank suspension of any main battle tank in the world. And although its top speed is not as great as some other vehicles, certainly when it goes cross country, that suspension enables it to maintain high speeds across country. Acceleration is important. If you do the sums, better acceleration tends not to get you to where you want to go that much quicker. But if you're moving in a threat environment and you want to move between areas of dead ground where the enemy cannot see you quickly, acceleration is really important. Ground pressure is important, and I'll say a little bit more about ground pressure in a minute, but that the ability to go off roads and tracks is really dominated by your ground pressure. Obviously, traction is important. Slopes are important. You need to go up steep slopes. You need to be stable on side slopes. One of the most demanding is actually going down slopes when you're towing and making sure you can actually control the vehicle and brake safely when you're towing vehicles. Those slopes are important. Step heights, the ability to cross obstacles, gap crossing, particularly smaller gaps. You really want to be able to cross them in the vehicle you're in rather than bringing up for scenes or combat bridging. Ground clearance, obviously important, especially off-road, deep wading, and perhaps a couple of less obvious ones until you look at the picture bottom right is is turning circle and size. And the picture at the bottom shows some jackal vehicles in Afghanistan in a typical village environment where you get these high walls around compounds and having some very constrained spaces where you have to maneuver. So certainly when you go into urban areas, that ability to maneuver in confined areas and have a good small turning circle is important. Ground pressure, this is probably the one people think about most in terms of armoured vehicle mobility. That ability to cross what we would call marginal terrain, whether that's sort of boggy terrain or snow. We've just been thinking about the Falklands conflict 40 years ago, and one of the success stories out there was the vehicles we use, these combat vehicle tracks, the scimitars and scorpions. Their ground pressure is lower than that of a person, so they could actually go anywhere you wanted to them. And there's sort of stories of commanders climbing down off the vehicles and going up to their knees in mud. But that freedom of movement is very important to terrain accessibility. And I think what's really important to bear in mind, it's not about where can a vehicle go. Vehicles do not operate in isolation. So it's all about where can a detachment of vehicles go. And one of the challenges that you can see it in the picture is when a vehicle drives along a area of boggy, muddy ground, it will start to develop ruts, and the first vehicle may be able to get through, but following vehicles can easily get stuck in those ruts. Mention sort of ground pressure. Ground pressure, nominal ground pressure, the weight of the vehicle over the area on the ground, it is not necessarily the best criteria to look at. There is a number of other criterias. One of the more sort of easier to understand is what we call mean maximum pressure. Always good to have an equation in a presentation, but the picture says it all. That actually, if you take a tracked vehicle or wheeled vehicle, what you will get is peaks of pressure under the wheels. For a tracked vehicle, they will be influenced by the track link size and width, but it's actually the average of the peak pressures rather than just the nominal overall pressure that's important. So that's a quick run through of mobility requirements. And as I suggested at the beginning, you very quickly run into having to make compromises. So actually, big vehicles are good. If you're in a big vehicle with big wheels, you can climb bigger steps. But big vehicles are more difficult to transport and they tend to be heavier. Narrow vehicles are good if you're maneuvering in confined areas, but one of the problems we have, particularly with wheeled vehicles, is they tend to be quite high, particularly if you're in a mine-protected vehicle with a V-shaped hull. You can end up with quite a high centre of gravity, which means if you're on side slopes or if you're going around corners quickly, you can easily have rollover. So narrow, good, but has its issues. Again, high ground clearance is good for mobility, particularly on very rough ground. High ground clearance is also good if there's a mine threat, it gives you standoff. But high ground clearance means a high vehicle, easier to see, harder to transport, and less stable. And again, if you want to cross big gaps, long vehicles are good, but a long, narrow vehicle is quite hard to steer. So we're already getting a number of mobility challenges. On top of that, there is the sort of the universal debate of wheels versus tracks, which particularly for lighter vehicles, if you're talking about a platforms over 40 tons, really you have to go tracks, but below that, there's always a debate. Do we have wheels or tracks? Wheels have significant benefits. Say, notwithstanding the benefits of band track, they give you better ride. You can go, particularly on roads and tracks, you can go faster with wheels. They're more efficient, so less logistic drag, and they're a lot less complex, so they can be more reliable. But they do tend to be bigger. Particularly, you start to lose hull volume to allow for steering. Your weight's over a smaller area, so the ground pressure goes up, and they can have lower traction. On the other hand, tracks, they are much better off-road. They've got a lower mean maximum pressure. They are very robust. They're more compact. They are more maneuverable. You can do neutral turns in a tracked vehicle, turn on the spot. But they are less efficient, higher noise and vibration, and more complex. So in general, tracks, like for like, give you better strategic and tactical mobility. Wheels give you better operational mobility. So we're left with this challenge. So what would we like? Ideally, we'd like a wheeled vehicle that has the same freedom of movement as a tracked vehicle. So a wheeled vehicle that can go on road and off road anywhere a tracked vehicle can do. And we'd like the wheeled vehicle to do a neutral turn. We'd like it to be compact for transportation, but actually we're interested in high ground clearance. We want that speed of movement. We want to be able to optimize our ride height for the threat. So we'd like a suspension solution that gives us a lot of flexibility in terms of geometries. So what are we doing? I'm going to talk about two specific activities. The first one's an enabler, really. So the British Army, through Army Headquarters, has funded a technology demonstrator. It's called Technology Demonstrator because it's number 6 of a number of demonstrators. But it's a hybrid electric drive demonstrator, and electric drive is a real enabler when it comes to improving mobility. And then within DSTL, working with our industrial partners, we've been doing work on novel suspension solutions to try and address some of the mobility compromises. So can we have wheeled vehicles that have the inherent benefits of being efficient, being able to go faster, having lower noise and vibration, but actually closing that terrain accessibility gap between wheels and tracks? But also looking at pushing the boundaries of ride and safety and obstacle crossing, because at the end of the day, we need vehicles that are inherently safe. We can't train all our army drivers to be rally drivers. So how can you ensure that these large, heavy vehicles can go fast, but do it safely? So TD6, say, it's aimed at hybrid electric drive. It's answering the question, what does hybridization deliver to the battlefield today? And in doing that, reducing risk for hybrid electric drive. What's happening under the program is 3 in-service platforms are being converted to hybrid electric drive. A manned truck, a Jackal, which is a light reconnaissance platform, and Foxhound, which is a small protected mobility platform. And the challenge has been to convert these to electric drive without impacting significantly on other areas of design. So for the manned truck, we don't want the mass to increase significantly. We want the same ground clearance. We want it to have the same load carrying capacity. And the work's been carried out by a consortium of industry, including prime contractors such as General Dynamics and Aerospace, but also supported by others. Magtech, they've provided the bulk of the electrical components, the motors and the generators and all the power conditioning and batteries, and Millbrook have been leading on the performance testing. So this slide shows the 3 platforms. So we got the MAN SV truck, just a diagram here, but you can see we have 2 electric motors driving the front and rear axles, and a good selection of batteries each side, we got a huge amount of battery stowage, probably more than you need, and with the engine generator, a large amount of exportable power. Foxhound predictor mobility vehicle. In this case, because of size constraints within the hull, we've gone for individual hub motors. So each of these wheels has one of these inside a hub motor. Jackal, this is Jackal. It's like a Land Rover on steroids. In this case, we've gone for inboard motors. So there's 4 motors, each with a gear chain driving the existing axles. So with these 3 vehicles, they're all series electric, but they've all got slightly different configurations. So, for example, we can see, if you've got hub motors with an increase in unsprung mass, what's that doing to the performance as opposed to inboard motors? So this works demonstrating the benefits of electric drive. Certainly, improved efficiency is one of the benefits. If you take the truck in the picture and you drive it up and down the motorway, it will give you no efficiency benefits whatsoever because mechanical drives are so good. But certainly on sort of more off-road routes, hilly routes, where you can start to gain benefits from regenerative braking, we're showing up to a 20% improvement in efficiency. And this is with a converted vehicle. This is without sort of doing things like changing the engine. So we've got a more efficient engine designed for running at constant speed. We got improved automotive performance. Electric drive gives you really good low speed torque. So in terms of hill climbing and hill starting, accelerating, really good. We can run on battery power only, so that gives you silent running, which operationally can be important. We got a huge amount of electrical power for onboard and offboard systems. And looking ahead, not so much to the TD6 platforms, but to new build platforms, electric drive does give you packaging and design flexibility benefits. So that's TD6, underpinning our risk reduction for electric drive. But the mobility risk reduction, this is an activity led out of the DSTL MOD research program. We're supported by a very good team led by Kinetic with the likes of Hortzman. Contract Innovation are real experts on control systems, Myra, Cranfield and Williams Advanced Engineering and Catalyst Corporation, who are a small outfit who specialise in synthetic environment modelling. And as I suggested earlier, what we're trying to do is really transform the performance of wheeled platform mobility. So we're taking the benefits of wheels, trying to build on the speed, ride efficiency benefits. But as I said, really try and push those benefits to the limit. Yeah, and that ability to go fast safely, and also that ability to manoeuvre rapidly and safely, but really to enhance the terrain accessibility. So we've been looking at a range of technologies. Central is very long travel adaptive suspension with multi degrees of freedom, and the ability to control wheel stations individually. We've got active ride. Because we've got electric motors, we can do individual wheel torque control. We've got all-wheel steer. And just recently, we've started to implement terrain sensing, which aims at improving the performance of active ride and reducing the driver burden. We've taken quite an interesting approach because what we're doing is fairly novel. And when we started this work, we didn't really know what benefits we could accrue. We wanted to do something which was affordable, but enabled us to really explore the technology. So we went for basically a 1/3 representation of a full-size 8x8 platform. So we've ended up with something that's about the size of a car. We went this route because it's affordable. We can use COTS components. It's easy to transport, but it's big enough that it's not a toy, that when people look at it, they can actually picture what it would look like full size. and this has brought a number of benefits. As a mechanical engineer, I'm fairly relaxed about the mechanical design aspects of this technology. More of a challenge is the control system. So in terms of control, whether it's a 1/3 or a full-size vehicle, control challenges are similar. By doing it at third scale, we can validate models for simulating full-size vehicles. And we can use it to assess some of the harder to model aspects. So things like sort of gap crossing and step climbing is fairly easy to simulate. Soft soil performance and the benefits of all-wheel steer are less easy to model. And it demonstrates capability in an age of PowerPoint engineering. To actually have something you can take the army out and show is really very powerful. We took a modular approach. We started off with configuration at the top, no engine, no drive, pumping the wheels up and down using a hand pump, and progressively we've added the electric drive. It's this because we don't need a long range. It's battery electric. We added the torque control. We added the active suspension control and the ability to control each wheel station. And most recently, we've added sensors on the front. And this approach has enabled us to manage risk in what is quite a complex solution. We're able to demonstrate potential early on, and it's enabled us to address reliability issues as we've gone along. So we've ended up with a robust and reliable platform. Some of the functionalities on it, electric drive, already talked about electric drive. It gives tremendous acceleration, like good low speed, high torque characteristics for hill climbing, for creep mode, and good acceleration. It's got long travel suspension with variable ride height, so that ability to optimize ride height for needs. So if you're going across rough ground, you can have a high ride height. If you want to be more stealthy, you can have a low silhouette, but also for transportation reasons, for a full-size vehicle, you can minimize the height to get into smaller transportation means. Got active suspension, giving a smoother ride. You don't get a lot of dive when you're braking, and you can compensate if you're on a side slope, which from a vehicle point of view means that it's much easier for the crew to operate the platform and use it as a weapon platform on the move. It's got wheel torque control, so better soft soil performance and draw bar pull. It's got all-wheel steer, gives a number of benefits, but in terms of basic driving, it gives you the ability to move safely in an agile way. If there's a threat out there, you want to present what's euphemistically called a non-cooperative target, and that ability to crabsteer, so you're keeping the front of your vehicle where your silhouette is smaller and most of your armor tends to be towards the enemy, but being able to maneuver from left to right, so you're harder to hit. But there's some really interesting things when you go off-road, and I'll say a little bit about how you can exploit all-wheel steer to improve off-road performance. We got a variable tracks solution, so you can move the wheels outwards, which gives you those benefits in terms of stability when cornering or on side slopes, but still that ability to go back to a narrow format for transportation or moving in confined areas. We can adjust the wheelbase to increase gap crossing, and just almost as a sort of sign, we can lift the individual wheels, so that gives us the ability to go up bigger steps. And if you have need to do servicing on one of the wheels, you don't have to jack the whole vehicle up. You can just lift that wheel station, or if a wheel gets damaged, you can just lift it out of the way. So great believer in pictures. So this next set of slides will just go through some of those capabilities. So Crabsteer, that ability to maneuver rapidly. The fact that you're not turning the whole vehicle to steer, you're just turning the wheels, enables you to maneuver a lot more rapidly. And I don't think the Army does a lot of parallel parking, but really good for moving into confined spaces, moving into hides. On the top right, we're showing a vehicle going into what we call flotation steer. So this is similar to Crabsteer, but you're actually driving the vehicle with the body of the vehicle at an angle to the direction of travel. And what that means is each wheel is following a different path. So by doing that, you're not disturbing so much the soil so much. You're not digging ruts for other vehicles to follow. And at the bottom, if you really want to be clever, we can lift the front and rear wheels and go into a diamond steer mode and turn on the spot. The active suspension and articulation control, we can actually cope with much steeper side slopes. You can see that in the picture. We've moved the wheels on the right hand side of the vehicle outwards. We're tipping the body to just adjust the center of gravity, so you can just see there how the vehicle is quite happy on a very severe side slope. Top right, we're showing the gap crossing, so we extend the wheelbase, and we believe we're getting about 50% more gap crossing. And it's not just the longer wheelbase. Normally, if vehicles are crossing a large gap, once the front of the vehicle has sort of moved over the gap, the nose will tend to drop. So if you're not careful, all you end up doing is hitting the wall of the other side of the gap. With this, we can lift the front wheels so that when you reach the other side of the gap, the wheels are actually at ground level, not below ground level. And the picture at the bottom shows step height benefits, the ability to lift the front wheels, drop the rear wheels, so the front wheels are effectively lifted off the ground. Typically, unless you've got a huge amount of torque and you don't mind damaging your tires, typically you can readily climb a gap which is about the radius of your wheels. And you can see in that picture we're clearing a step which is twice that. And again, we're using the flexibility of the suspension to make sure we're not actually bellying on the corner of the step. And then active ride. If we want to operate at high tempo, we need vehicles which are stable on the move, so the crew can operate, they can communicate, they can use their sensors, and they can operate their weapons. So there's two pictures on the left-hand side show the vehicle at the top running without active ride on, and the one below with active ride on, and it's going over a sine wave course. And what the active ride does is helps keep the body a lot more stable. And we can also have self-leveling, which you can see on the picture on the right. This is a bit of an aspirational chart, but it's showing what we're trying to achieve with the work we're doing. So if you look at the inner orange part of the spider diagram, that's looking at wheeled platforms, and clearly compared with tracked vehicles, which are shown in green, they're a lot quicker on roads. You get a lot of benefits. But in a lot of other respects, tracked vehicles are better. They give you better obstacle crossing. They give you much better soft soil performance. Tracked vehicles tend to be more stable because they have lower center of gravity and can often give better cross-country ride. But what we're doing with the sort of technologies we're looking at is to firstly push the performance of wheeled platforms, so that ability not only to go fast, but to go fast safely. And although we can never match the performance of tracked vehicles in terms of off-road performance, we're certainly looking to close the gap and by giving better obstacle crossing than tracked vehicles, we think your actual freedom of movement will be significantly better. So that's our sort of, in a simple illustration, what we're trying to achieve. So that concludes my presentation, which hopefully been important. And so if I can work the technology, I'll switch the slides off and we can move to a question and answer session.
Thanks very much for your presentation, William. Graham, are you on the line?
Yeah, if I speak now, can you hear me okay? Can you?
Yes, loud and clear.
Okay, that's great. So so perhaps I'll just do a quick introduction. My name's Graham Wilcock, and I'm the vice chair of the Germany group of the IMechE, and it's us that have sort of strong-armed William into delivering this presentation tonight. And then I fortunately had the usual IT problem, so I've had to sort of backtrack and set things up on my mobile phone. But yeah, William, thank you very, very much for that presentation. I thought that was really fun. There's a few questions coming in, and I think I'll give over the first question here to Malcolm, who's asking about the kind of battery technology that you're using with this technology demonstrator, and then also if there are any special challenges that you experience or you envisage with battery performance or safety for armored vehicles.
Okay, on the battery technology, for the mobility test rig, we're just using sort of readily available technology. For the TD6 demonstrators, they are lithium-ion batteries, C1 and C2 cells. We are obviously looking with great interest at the safety issues of lithium-ion batteries, and it's an interesting topic. In some ways, you're comparing lithium-ion batteries with conventional fuels. Talking to the experts, the main challenge with lithium-ion batteries is really a trading issue and understanding where the risks are. So we know that lithium-ion batteries, if they get damaged or in certain conditions, can go into thermal override and can catch fire. From an armored vehicle, which would normally have a lot of diesel, a lot of explosives, you can say, are they any less safe? And the answer, the sort of conclusion we're coming to, is probably not if you know what you're doing. And there's some sort of interesting challenges with lithium-ion batteries. For example, if they do catch fire, it's very hard to put the fire out. And damaged lithium-ion batteries, even if the fire does go out, they can reignite several days later. So the main, we think the main thing is understanding the risk, having the right training so people know how to react if some sort of thermal runaway event happens. Hopefully that answers the question.
Yeah, I think so. But I just add on to that, my background the last 4 years was in automotive testing, and the company I was with at the time had just moved into battery testing. A lot of this technology for military applications is coming over from the automotive industry anyway. But the automotive industry itself is still in the early stages, really, of hybrid electric and full electric drive in terms of the testing and the specifications required. So there's still a lot of work to do on the civilian side to sort of understand exactly what we're expecting from this technology. So I think that the military is still, we're certainly not behind on that. It just needs a little bit more understanding, I think, of the specific military application of it. But what you finished off there, William, was talking about sort of training, and there's a great question here from John, who asks, basically with these vehicles and the increased capability that they're giving, ultimately, if it's a manned platform, certainly, someone's got to crew them and drive them and understand how to operate them. So do you see them bringing an increased training demand and increased driving ability over what the sort of current military would expect?
Yeah, I think that there inevitably will be an increased driving demand because you are doing so much more. I think what we need to do is minimize the training demand. So in going forward, what we want to do is optimize as much functionality as possible. So it's early days, but we've on things like sort of step height. We've done lots of trials. On mobility test rig, it's basically remote control, and you have someone with a remote control PlayStation type controller who controls the vehicle. We just moved to the stage where, with the sensors on the front, the platform itself can detect there's an obstacle coming up, can slow the vehicle down, can work out the height of the vehicle, and raise the front wheels to the correct height. So certainly with a lot of technology associated with autonomous driving, we think we can do a lot to minimize the increased burden particularly on the driver, but also actually make the platform safer, because that is a very big issue for the army. Safety, rollover has always been a big issue with vehicles, but if with the sort of technology we're looking at, you can detect, if you're on a limiting side slope, detect it if things are starting to go wrong, and automatically adjust the track, or automatically reduce the ride height to compensate. So in some ways, there will be a training burden because these vehicles are a whole lot more capable, but actually trying to minimize that as much as possible.
Okay, great. There's a question here, and I'll say perhaps if you might want to answer it as a sort of big picture rather than detailed, but basically Seb is asking what the sort of biggest learning point you've observed or seen so far from the conflict in Ukraine, specifically in regards to high mobility. The work that you presented today, is that something that you're really taking away from?
It's very difficult. I'm not in the military, and there's lots of armchair tactical people around who think because they played World of Tanks, they know all about armored vehicles. I think to me, what's happening in Ukraine is pointing to the need to operate in a very different way. And you could argue, and it's very difficult because the Russians clearly got their tactics and the whole approach totally wrong. They've totally failed in what we'd call all arms warfare. But arguably, you could say if you had wheeled platforms using the sort of technology that we proposed, they could have driven to Kiev incredibly quickly and operated sort of well within the what we call the threat decision cycle. So if there is a lesson to be learned, it's traditional slow moving armor does give a chance for the opposition to respond. But it does sort of raise the question, do we need to move back to very maneuverist warfare, really exploiting ability to move very, very quickly? So that's very much a sort of a non-military view.
Mark is asking that, as you explained, TD6 is really a hybrid solution, so it maintains the internal combustion engine. It's just adding that electrical drive capability. With the MRT, how are you charging the batteries. And if you were to sort of scale this up to a full size model, how might you see that developing?
Right. I think you have to be totally realistic and say, if we're talking about armored fighting vehicles, particularly sort of 30 tons plus, battery electric is not viable for the foreseeable future. So the sort of model we're using for our future concepts is to say, certainly for the next 10 years plus, hybrid electric is the only viable option. In the future, we should be able to move away from diesel as the range extender, possibly to hydrogen. I think the lessons I'm getting from the commercial world is actually burning hydrogen in an internal combustion engine is probably a better way to go than hydrogen fuel cells. But the aspiration is, as battery technology improves, you can move more and more towards battery electric rather than hybrid electric. That still leaves the question of how do you recharge the batteries and how do you do it quickly. There's a lot of debate on that. Actually, miniaturized nuclear does actually look very promising and could be quite a safe option, but sort of has the N word in it.
Yeah. Okay, great. There's a question here from Alex, and he'd already sort of posed this to me last night, actually, and I've been kind of thinking about it over the last day or so. So he's asking about where do you see the challenges of supporting EV vehicles or vehicles with EV technology over complex terrain. But I know that he was also interested in the aspect of recovering damaged vehicles. So if the military, is really important that you're able to hook up and tow a vehicle, either suspended tow or a straight line tow. What sort of challenges do you see with this type of hybrid electric drive?
That's something we're very much looking at. The current plan is, with the demonstrators we've got, as I said, they're undertaking performance testing at Millbrook. The next stage is to upgrade them a bit and then move them to the Armoured Trials and Development Unit. And the towing one is an interesting one that basically, with the platforms we got, you can tow them safely a few tens of meters. So if a vehicle was bogged, you'd easily be able to bring up a recovery vehicle and tow them to firm ground. It certainly wouldn't be safe to just hitch them on the back of a recovery vehicle and tow them on roads, because effectively your motors become generators. So those things, we haven't got a definitive answer, but we, as part of the work with the Army, we will be exploring what's the quick way of making safe electric vehicles so they can be towed. I think linked to that is, if a vehicle is damaged, what mechanisms can you have for ensuring that the vehicles are safe and the batteries aren't about to go into thermal overrun. We don't have all the answers yet, but it is definitely on the list of things to do that we're exploring with the Army.
Yeah, sure. Because I mean, I guess from the sort of other side, potentially there's some interesting advantages there if you're towing a vehicle that is otherwise, okay to tow. If you can just feed that essentially now charging motors into your recovery vehicle, then there may be some interesting advantages there to sort of power sharing. It's a question about the cooling of the motor.
Or if some of the motors are still functioning in the thing you're towing, again, you can power those and add to the attractive effort.
Yeah, it's probably I'd be interested in what Alex, that posed the question, thinks about it. He's a recovery mechanic, so I'm sure he's thinking about it a lot as well. Yeah. I've got time for probably a couple more questions, I think. Question here from John, who's just asking about the timescales of these type of technologies. are they really mature enough to go into service now?
Right. Hello, John. I recognise the name. In terms of timescales, hybrid electric drive is probably right for getting into service fairly quickly. So the Army are exploring the potential for converting vehicles now, and I think personal opinion is, you do not want to go out and convert the whole fleet of man trucks or jackals in the British Army. That wouldn't be cost effective. But for particular uses, converting a subset of the fleet is very attractive. And I think, if there are military spec drive motors out there. So, within 3 or 4 years, if the will was there, you could bring electric drive into Army service. The sort of technologies we're looking at on the mobility test rig, again, some of those technologies you could exploit very quickly, but the bulk of our work on the more advanced solution is sort of aimed at solutions for new build platforms, sort of 2030 plus.
Yeah, I think perhaps there's a bit of a Prius moment still to come. So the adoption of electric drive technology within civilian automotive vehicles, it was always there, but then sort of Prius came along and it sort of took off from there. I think in my mind, sort of late 90s, early 2000s. Then it's, I think once a military, any military sort of puts this in their specification for a new project or really starts trialing it on a very large scale, then I think that'll be the sort of inflection point, and then things will go from there. Afshin asks a question about the expected increased power to weight ratio of modern wheeled and tracked vehicles, and the greater demand that's placing on suspension systems. And if you think that the current suspension technology can cope with that expected demand, both in terms of cost and reliability. So you're talking there a lot about the sort of suspension of vehicles and how that can improve mobility and the quite advanced suspension there from a Horseman on this demonstrator. So do you foresee that being an issue in terms of the cost and reliability?
It's certainly an issue. I think we're yet to determine how much of a problem it is. One of the if you take a typical 8x8 platform, you can say each wheel carries an eighth of the weight of the platform, and you put in a jolly good safety factor for shock loads. The sort of technologies we're looking at could mean that you're carrying the whole weight of the vehicle on full wheels at any one time. So that infers your suspension needs to be a lot stronger. The counter argument to that is because we got the active control and because we're sort of sensing the ground, we're actually reducing the shock loads going into the suspension. So the likely is, and we really need to sort of prove this, and the next stage we're working on is how we can upscale the technology. But the view is actually with the sort of active control we're looking at, although the static loads may be higher, the dynamic loads won't be sort of proportionally greater. So the design challenges may not be as significant as you might first think, if that makes sense.
Yeah, it does. Yeah. I think we'll perhaps finish off with this one last question. Alex has posed two questions, and they're on a sort of similar sort of theme. So, Alex, with respect, I'm just going to sort of summarize them a little bit. We've been looking here really at wheeled platforms. The logical question is sort of, where do you see this is there move into tracked vehicle technology as well? How do you see this technology moving into the tracked segment?
The reason we've looked at wheels is because at the end of the day, within the UK Ministry of Defence, we have a limited research budget, so you actually put your money where the most benefit could be gained. And I think that there are things you can do to improve tracked vehicles. The obvious one is to move to band track. There's a lot of work has been done on active suspension for tracked vehicles, which can significantly improve ride. But I think the bottom line is we've shown there is an awful lot you can do to improve wheeled platform mobility. The scope for improving tracked vehicle mobility and overall performance is a lot less. So that's why we focused on wheels.
Yeah. Okay. Great. I think that's probably all the time we've got. All the time we've got for questions. What I would say is that on the screen in front of you, you should see a resources tab, I think, and in there I've put a link to a LinkedIn post. If you follow that, I thought it might be nice just to sort of follow up if you've got questions that you haven't been able to get answered, or you've got an interest in sort of connecting with people. We can sort of keep this conversation going for a little bit, and people that are interested can sort of connect a little bit more. It's one of the sort of networking bit kind of falls out from these type of events. Pat has asked about if a copy of these slides can be shared. We sort of discussed this before, William, and I think if people want these slides, if you can sort of reach out, either to me or William directly, you can probably find us both via LinkedIn, or if you email the IMechE, then that request will be passed to me, and I can pass it to William as well, and then they can be shared, I guess, under your direction, William.
I think the slide's obviously been clear for this presentation, but if we're sending copies to people, we'd really like to know who they're going to and why.
Yeah, sure. And then this was a really great presentation again, William. You gave a presentation to the IMechE about 18 months ago on your work at the Military Vehicles Research Establishment. I think it's only fair for me to sort of give you a small plug to your book that's available on Amazon. It's a fascinating read about the work that was done there at the research establishment. It's called the Tank Factory. Thank you very much again for your time. We really appreciate you giving your time to the institution of mechanical engineers, and thank you very much.
You're very welcome.
Great. Then I think that's everything. A copy of all your questions are going to be sent to me anyway, and I'll do my best to pass them on to William and try to get you answers anyway. But like I say, that link to the LinkedIn post is there. And I think that's all, apart from to thank you for dialing in, and apologies for my IT issues at the start, but I shall wish you all a pleasant evening. Stay well.